So E4S, the Extreme Scale Scientific Software Stack, is an ecosystem for science, and it's a HPSF and a community effort to provide open source software packages. And it has built a comprehensive, coherent software stack. It provides a curated Spack-based software distribution of over 100 different HPC packages, of AI/ML packages, and we have containers, base containers and full featured containers with support for GPU runtimes from GPU vendors such as NVIDIA, Intel, AMD, and we also have E4S available on cloud platforms including Google Cloud, AWS, Azure, and Oracle cloud infrastructure. There are other tools that E4S provides to chain to Spack instances, so you can install new packages while retaining the dependencies from a centrally installed Spack installation. We have tools to allow you to distribute your application in binary form by allowing you to substitute the MPI in the containerized application with the system MPI, and also tools to allow you to customize your container images by adding other tools to a base container image. So here is an example of E4S with many of its tools based on Spack. And today I want to describe how do we build the distribution, what kind of CI infrastructure is used. You can go to e4s.io and download our packages. E4S, as you know, uses the Spack package manager for software distribution. And as Todd showed earlier, that there is a pretty complex dependency over here. The red boxes are the top level products, the packages in E4S, and all the others are the packages that need to be installed. And clearly, it's not something you can do manually, one package. So we use Spack, and Spack provides a good way to describe the compilers, to describe the versions of a package, such as Spack install tau version 2.34 with the GCC compiler at version 11.2.0, and then you can turn on variants like MPI, Python, and specify which MVAPIC distribution, which version implements the MPI. And so you can get into great detail about the dependencies and how it should be configured, and learn more about Spack at spack.io, of course. Now, when you create a new pull request, Spack emits a large number of jobs from gitlab.spack.io, which are run on AWS as well as on Frank at UO. And today I would like to just describe how we introduce a new package, what are the E4S repositories, the container recipes, and what kind of CI is performed at the E4S level, and what is done at the individual package level, and how the HPSF CI integrates with all this, and how we can track job failures. So first of all, the GitHub site is the github.com E4S project, and there are several environments over here in the Spack GitHub site as well. And you can see the stacks that are defined over here that include E4S and E4S ROCm and one API, Cray-Rel, and so on. Now this is how you can communicate with the E4S team. There is an E4S, there is an email address. You can describe your new package that should be included. You can create a pull request, and here are some examples of issues that have been reported on the Spack site and curated. You can see how an E4S package gets introduced at that site number 1. You can see that there's a new product that will be at the ISC release, the libseed package, and you can see how this issue gets created, and here is an issue saying that please add libseed to the E4S distribution, and then it is then integrated with our tests. And here is how the CI jobs ensure that new specs build properly. You can see the branch over here, and here is a actual spack.yaml file which is updated, and you can see the libseed entry for the CUDA arch equals 120. Now this is work in progress. This has not been released yet. This is on the Blackwell GPU from NVIDIA, and you can see the CUDA arch. Here is a libseed for a ROCm version, and there are different targets for different GPU architectures where we keep the spack.yaml file, and this new PR then triggers off a large number of jobs in our CI system for E4S. So you can see that there's a build for AMD 64, there's a build for ARM 64, and then PPC 64LE over there. And each job builds the new libseed root spec on the target platform and then pushes the build to a SPAC S3 build cache where it is stored. And then you can see over here how this build cache auto push happens. There's a SPAC mirror add E4S command there. It goes to cache.e4s.io where the package is then stored in the binary form, and it's then pushed to the build cache. And this is an example of the Power 9 runner for PPC 64LE on Frank at University of Oregon. But you can see over here the recipes for the different container images. This is x86 64, ARM 64, and PPC 64LE. So it goes through a large number of tests as well. And here is the package setting with the CUDA described over here with CUDA 12.8.0. This will allow us to build a container which is based on GCC and say mpitch 423. And you can see the mpitch description, the package description for CUDA, and we are using an externally installed user local CUDA 12.8 here. And then there are the concretizer settings over here to say that reuse the packages from the build cache. We describe the target as MTI and with CUDA 12.8. And then there is the compilers.yaml, the modules.yaml. These are all there in the GitHub site. You can see the description for each CUDA 80, 90, 120 for the A100s, the H100s, and the Blackwell GPUs. And then these are the SPAC environments, and then the compilers and the modules configuration and the externals that are involved with this. And then the container is built. Here is a recipe for that. This is the CUDA target. You can see how you have all these chained commands where we take this set of packages which were described in that spack.yaml. We create the make file, and then we build it in parallel, a 32-way parallelism with this SPAC deb file feature. So we create the make file, and then we install it. And then after this is done, we also do a spack-e.install just in case there are any issues with the parallel build. It again simplifies that. And here is the pipeline. You can see the full images being created here on AMD 64 with Ubuntu 22.04. There are separate images. So this time we are going to have a separate image for CPU only products, and then each GPU product to reduce the package bloat. And you can see all the images, the Docker push, and then the Singularity builds where we create that image. And the current release methodology is that it's a biannual release process on multiple GPU architecture. There is NVIDIA, AMD, and Intel GPUs, and we build for host 64, ARM 64, and PPC 64LE, and that we have a E4S test suite that then exercises all the built packages, and we can see the results of the test suite. We create a binary cache for each release. In this case, the last release, binary cache is pushed to cache.e4s.io/24.11 for the supercomputing release. And then the Spack environments are used to generate these container images. And there are some software quality efforts based on the automated CI that is directed at maintaining this distribution. You can see the details of the cloud pipelines over there. And there are requirements for such a CI system. So what hardware do our HPC projects typically need for CI? We do need GPUs from multiple vendors. We need diversity of operating systems and programming environments. And we require different network interconnects for testing. And we typically have 2 nodes that are identical, and they have multiple GPUs, and we exercise the multi-node examples over there. And we use Frank at the University of Oregon. This is the URL for Frank, oss.uoregon.edu/Frank. And you will see the types of machines we have over here with different GPU architectures. Here are the names of some of the machines and what kind of GPUs are available over here. And some of them are very capable machines. And you will notice that we have a large number of CPU cores as well. Some of them have 96 cores and 2 sockets with 96 cores. Some of them have 72 cores, like Grace systems, and 2 sockets of those. So that's like 144 cores. And all the different GPU architectures are there. Our goal is to have every GPU architecture from every one of those 3 vendors, NVIDIA, Intel, and AMD. And you can see the list of machines over here. We also have support for Macs. We have M1, M2, M4 Pros. And here is stats.e4s.io. This site can be used to see what errors we are recording. You can see what jobs ran, how many jobs ran on which GPUs. So between AWS and Frank, since we started collecting the data in late 2022, we have run over 9 million jobs on these systems. So you can see the 9.2 million, and you can see just last week what kind of jobs ran. So this is a listing with 12 different GPU architectures and how many jobs ran in each week. And this is a typical pipeline. This is a typical job. You can see that this is a nightly regression test case for Trilinos. And in Trilinos, you can see that there are 4 stages. This is passed. And if you click on that, you'll see the actual architectures, all 12 of these GPU architectures that are exercised every night. Here is a sample job. This was run on an MI300A GPU for 44 minutes. And there were how many? 448 tests that were run on the GPU on the MI300A. And you can see that it took about 44 minutes. And it's using the ECP E4S container from Docker Hub. You can see the E4S container that was used to build this CI. And you can then go down and click on this and see the artifacts. You can download it. Here is a sample output, the detailed output of the Trilinos job that was run. And here is an example from Cocos. Now, you can see that there are 6 different GPU architectures, how many tests passed. And it's important for us to realize that in any kind of a CI environment with GPUs, there are bound to be failures. And the failures are just a fact of life. And you can track those failures. Here, all of these tests have passed. And this is a set of jobs that were launched when a pull request was created. And before the pull request in Cocos can be merged, it creates all these jobs on those 6 different GPU architectures on Frank. And then you can click on it and see. Here is an example of a pipeline where I have an error that takes place on a GPU, while 5 of these other jobs ran to completion successfully. And then you can go and look at that failed job and see that the following test failed, and the 15th test over there has failed. And you can see exactly which test failed. And within that 15th test, you can see that there are many other tests embedded in it, like they are running 29 tests over here, 4 tests there. All of those passed, but there was one test which had a timeout. And so it failed over there, and the whole pipeline gets affected. And here is another case where on an Intel GPU, all the other cases ran, but here it got an error, and you can see the backtrace in the detailed output. And in another case, you can see there is a failed error saying regular expression found in output, and then there is a failed test. So these are the kinds of examples of tests that can fail at a package level. They are, of course, tests at the E4S level, at the package level, and this is a successful run, and then this pull request can be merged easily because all the tests passed. But what happens when the failures occur? And you can see the different kinds of jobs that are run on Frank, and we have a detailed listing of the average runtime, the number of jobs, whether it was run at the University of Oregon on Frank or on AWS, and the list of how many jobs ran. This is just in 24 hours. It's roughly 50-50, the split between the AWS and University of Oregon. Sometimes it goes up or down. And you can see in the last week what was the split, how many jobs of what kind ran on which system. And you can see the detailed statistics that are recorded in stats.e4s.io. But it's not just the number of jobs, but also the failures. So we record the failures. You can see in the last 24 hours which jobs failed, how many at the University of Oregon, how many on AWS, and what runners were affected on AWS. You can then see at the Spack site, the grafana.spack.io, detailed information about each runner and what happened over there. You need to have a GitHub login to be able to access this information. And then there is a load monitoring system which is installed on Frank. This is the Ganglia output. So you can see of all the nodes that are running these CI jobs, what is the load on any of those nodes, and you can then click on that and get detailed information. So I would like to say that E4S contributions are unlike those of most other projects. The overwhelming majority of the commits that contribute to E4S are pushed to the Spack or a member package repo. You can see examples of recent PR and a lot of the significant CI that is involved before cycle, and how package contribution takes place. And if you are interested in getting involved with the CI effort, please talk to us. If you're interested in trying out Frank GPUs and platforms, please talk to us. I would like to thank the US Department of Energy Office of Science and our projects, the PESO project in particular, and the DOE SBIR program, HPSF, and the Exascale Computing Project. I'll take any questions.
Thank you, Samir. I think we have time for probably one question, depending how long, maybe a second one. Ken?
Hi, Samir. What exactly does it mean to have a project in E4S? Is there a Spack meta package that lists all of them, or
so
what does that mean?
It's on our repo, and then you can see the YAML file which has the listing of all the packages, but we also have the full list on our E4S web page. And there are some community policies that are involved with joining, and there is the full list of packages over here, and you can see which packages are member packages, and you can go down to a particular package website. You can see the summary and the license and the change log, and this is information that is raked from the repo every night for that particular package. So you can see this full listing.
So what does that mean for someone who just wants on their, say, their local university cluster, wants to install the E4S software stack?
So they can go to the download page. They can get the actual, go to the download page, then they'll be able to pick up the spack.yaml file, they'll be able to install Spack, and there are instructions over here that describe how that's all done. So you can build from the Spack and do a bare metal install, and you can go to the home page, go to the documentation, and install it. It's all there on the web page. There are detailed instructions. You can look at the release notes for that.
All right, thank you, Samir.
Thanks.